driving along unhindered by traffic. You want to get from A to B. If there's no other traffic, there's hardly a problem. You drive at the speed you find comfortable and safe. If you break no laws, on this road that means anything up to 70 miles per hour. It's a little more complicated, but not much, if you're driving with some other traffic. You overtake when you can, or if not, you follow behind. But how far behind? What happens if the traffic is heavy? On a busy road with people in a hurry, vehicles often get very close together. But it's not a good idea to drive bumper to bumper at 70 miles an hour. Why not? You don't just want to go from A to B, you want to arrive. And that means that you want to drive in a way that avoids the possibility of a collision. In this program, we'll take that as a modeling problem. Somebody somewhere once modeled this problem in just the way that you can now. So how do you start? You need to look for variables in the problem that you can relate as the first step in your model building. If the problem is to avoid colliding with the car in front if it stops, the first thing to find out is the distance you need to stop your car in. And that clearly depends on the speed you're going. And so a natural first step in the modeling process is to relate the speed of a car to its stopping distance. We want a formula for how far you travel in terms of your speed when you begin to brake. Assume that you take time to react, the thinking time, and then you brake. What symbols do you need? The overall stopping distance, S, measured in meters. Your initial speed, V meters per second. Your thinking time, T, seconds. And when you apply the brakes, a constant deceleration. Its magnitude is D, say, that's in meters per second squared. It's against your direction of travel, so it's an acceleration of minus d. So what is S in terms of V and T and D? During the T seconds thinking time, at V meters per second, you travel VT meters, the thinking distance. Then you begin braking, and now this formula applies. The final speed is 0, the initial speed is V, and the acceleration is minus d. Rearranged, that gives the braking distance. Add the thinking distance to the braking distance, and you get the overall stopping distance. That's the formula. But now you need some estimates of the thinking time, t, and the deceleration, d. What might d be in practice? Research suggests that on good roads, with good brakes and good tyres, a reasonable figure is 2/3 of the gravitational acceleration. Perhaps it's just the attraction of a symmetric-looking formula, but other research has shown that under laboratory conditions, your reaction time will be around 2/3 of a second. At a legal maximum of 70 miles an hour, then, that's about 32 meters per second, you'll think for 21 meters and brake for a further 75 meters. Overall, 96 meters. This, of course, is about how drivers should behave under optimal conditions. It's not about how drivers do in fact behave. Like the driver of the white truck approaching this stationary traffic. So how do people behave in reality? This stream of traffic is moving at around 30 miles an hour. At this speed, the stopping distance is 23 meters. Look at this car. 23 meters is to here, just acceptable. As for this pair. But of the cars travelling in this direction, most are travelling too close. People just don't drive as far apart as they should, according to the formula. And people do have accidents. So why don't people drive the way the stopping distances suggest? One reason is that it's far from easy to judge distances on the road, even if you are aware of the advice in the highway code. At this speed, the highway code advises 96 meters. If you started braking at the sign, where would you come to rest? Here? Here? Or here? Watch. Actually, it's to here. But there are other reasons why the highway code stopping distances might not tell the whole story. On a motorway, you don't normally need to brake to avoid stationary traffic like this. What does happen? A driver sees an emergency, thinks for a while and then brakes. We've got a model for that. The second car will respond to the brake lights of the first car. Here it is taken apart. Car 1 sees the emergency and thinks for a while. Car 2 sees nothing yet. Now car 1 begins to brake, and car 2 begins the thinking time. When car 2 begins to brake, car 1 is already partway through its braking. At 70 miles an hour, it's 21 meters into the 75 meters required, and only has 54 meters left to go. What happens next depends solely on how far apart the second car was following. Too close, and they collide. Far enough, and they come to an orderly rest. Here's a steadily moving stream of traffic, all travelling at the same speed and the same separation. Watch the point on the road where the first car applies the brakes. If the separation is large enough, the second car will begin braking before it reaches the same point. If we assume identical conditions, the second car will come to rest safely behind the first, as will the remainder of the queue. But with closer separation, car 2 will have passed the crucial point before it can begin to brake. That's a recipe for disaster. The critical situation, then, is when each car brakes at the same point relative to the road. How far apart would they have to be? We have an answer for that. VT meters, or 2/3 of a second. But driving at exactly that separation gives this rather unwelcome picture. So you have to allow for the car lengths, at least. Even with that adjustment, that's a minimum figure. The 2/3 of a second reaction time is for alert drivers who are looking ahead. The braking distance is for well-maintained cars. You need to drive a lot more than 2/3 of a second apart. The recommended separation is actually 2 seconds.
Accidents like this happen too often, but many could be avoided if drivers would only keep a safe distance from the car in front.
In the early 1980s, a safety campaign was launched based on this 2-second rule.
So if you're not sure how close is too close, try the 2-second rule. Select a marker on the road ahead, such as a bridge or sign, and then when the car in front passes it, count 2 seconds. If you reach the marker before 2 seconds are up, you're too close and should drop back. Next time you're traveling on an open road at a speed of 40 or more, try saying to yourself, only a fool breaks the 2-second rule. It takes just 2 seconds to say. Only a fool breaks the 2-second rule. Try the 2-second rule. It'll help you keep your distance, and it could save your life.
There's no direct relationship between the 2-second rule and stopping distance. At low speeds, the 2-second rule is more cautious. Above 40 miles an hour, it suggests a smaller separation. It reflects the reality of motorways, and it reflects the reality of people. A rule people would obey is preferable to a better rule that is usually ignored. But now we've got two models, a dynamic model of stopping distance, which we've seen not to match observed driver behaviour, and the 2-second rule. Are drivers more likely to follow the 2-second rule? We can easily see what happens 2 seconds later. Watch the ghost image of the car in the left-hand lane. It's too close to where the white van was. But let's just take stock of where we've got to. You want to get from A to B safely. That means driving at a suitable distance from the car in front, depending on your speed. The two models so far suggest that at 70 miles an hour, you should keep 96 metres behind, that's from the stopping distances, or 64 metres if you're following the 2-second rule. Of course, there are a lot of assumptions we haven't looked at. We're assuming that 70 miles an hour, which is the absolute legal maximum, is a safe speed. That's just not true in bad weather, rain or fog for instance, or if your car is not well maintained. And you'd feel even more uncomfortable if the vehicle on your tail was a heavy lorry instead of a light car. TRL, the UK Transport Research Laboratory, has been active since 1933 in trying to improve road safety. Close following, or rather over-close following, has been on their agenda since the late 1970s. In 1990, they imported a tested idea from France. Two sections of the M1 motorway were marked with chevrons.
The first site was installed on the M1 motorway in Leicestershire. As you approach a site, you'll see in the middle distance the start of the markings on the road surface, and at about the same time you should be able to read the large roadside sign that says "Keep apart 2 chevrons." As you drive over the chevrons, you'll see them repeated at frequent intervals for a distance of, in the remaining case in Northamptonshire, of 4 kilometres. And there are 3 of these large roadside signs to remind you what you should be doing as you drive over them. Now, the ideal situation is, as you drive and you're following the vehicle in front, that you can clearly see 2 chevrons between you and that vehicle at intervals. You won't see that all the time. If you can only see 1 chevron, then you are definitely too close. If you can always see 2 chevrons, or more than 2 chevrons, then you're a very safe distance apart. The idea of the chevrons is to give you a sort of scale on the road surface to measure your following distance again. It's not something people are very good at normally. They have a speedometer in their car to measure speed, but nothing to measure distance.
The purpose of the chevrons is to keep drivers 2 seconds apart. So, how is their spacing determined?
Well, the chevrons are designed to cause drivers to drive 2 seconds apart. Now, that will only work at one particular speed, and a typical speed for taking across the 3 lanes of the motorway is about 65 miles an hour. That amounts to 58 metres at that speed. Now, the actual way that 58 metres is made up is a number of elements, and the first of them is the amount of road space that's cut off by the bonnet of your car. And we did a few trials to get a rough idea of what this was. We sat 2 different size drivers in a number of different vehicles, and an average figure came out to be about 5 metres. In order to be able to be sure you've got 2 chevrons, then you need some road space before and after the 2 chevrons that you can see. And we allowed a car's length, roughly another 5 metres for each of those distances. The chevron itself is 3 metres long, and you can see 2 of them, so you've got 2 of those plus the distance in between. That's, in fact, another 40 metres. So the total comes to 5 plus 5 plus 3 plus 40 plus 5, which is somewhere about 58 metres, I hope. If, as you're driving along, you can only just see 2 chevrons, that's to say 1 chevron's just about to disappear under your bonnet just at the same point as the chevron has appeared from the rear of the car in front of you, then that's a separation of about 1.6 seconds. Now, ideally, we'd like 2 seconds because that's the highway code advice, but we're reasonably happy with a minimum of 1.6 because of some work we'd previously done with close following warning signs at Ascot. And there we had a sign which was illuminated when the gap between vehicles was less than a certain value. And we started off with 0.7 of a second, and we gradually increased that 1 second, 1.3 seconds, 1.6 seconds, and we found that the driving behaviour gradually improved all the time until we got from the 1.6 to 2 seconds interval, and then it went down very slightly. So we felt that somewhere around 1.5 seconds, drivers were quite happy with that advice. When you go beyond that, they start perhaps to think it's a little bit long.
Installing chevrons can be done without closing the motorway. A mobile lane closure team works steadily in the direction of the traffic flow, marking out the site ahead of the team that cleans the surface and actually lays the pattern. So it's cheap to install. But is it cost effective?
Well, we compared the cost of laying the patterns, depreciated over their life, putting up the signs and so on, with the likely savings in accidents. And in fact, it turns out that you've only got to save half an accident for these to be cost beneficial. In other words, the cost of installing them is only about half the value that we presently put on a motorway accident. Now, the most difficult thing is to show that an accident change has been statistically significant. In other words, that the numbers haven't arisen by chance. So virtually any accident saving that we can show to be statistically significant will also be highly cost beneficial.
The first two sites were closely monitored experiments to determine just how cost beneficial the chevrons could be. One site was temporary and was allowed to wear out after 6 months. The other is permanent, and monitoring continues. The purpose of chevrons is to reduce accidents. So to judge their effectiveness, we should really count accidents. But accidents don't occur very often, fortunately, and so it's difficult to tell whether any changes are due to the chevrons or to chance. But close following is easily measured, and is behavioural data about how drivers react to the chevrons. It acts as a proxy for accidents, and that's what the TRL actually measured.
We looked at behavioural data at 3 points on the motorway, and the data we were measuring was the speeds and particularly the gaps between vehicles, the spacings between vehicles. And we did it initially well up the motorway before you get to the chevrons, just down here, which is about halfway along the length of the pattern, and about a mile after the end of the chevrons. At each site you would have seen loops cut into the road surface, measuring speed and spacing in each of the 3 lanes, and just a simple grey cabinet beside the road with the recording equipment in it. Now, we made these measurements at a number of intervals, initially of course before there were any chevrons there, and then roughly at 3 monthly intervals up to 12 months. Initially you'd expect quite a large novelty effect with these sort of measures, and with time you'd expect this to decay away slightly to hopefully a level which is a little bit less than the before, or at least substantially less ideally than the before level.
You get your own chance to monitor the behaviour from these pictures collected soon after the installation. How many cars are doing acceptably under the 2 chevron rule? You probably have your own questions about the design of the experiment. Why aren't there chevrons in the outside lane? And shouldn't they be spaced differently in different lanes to reflect the different speeds?
Obviously you could possibly expect different spacings in different lanes because the speeds will be slightly different in different lanes. But in fact the differences are so small that we felt it was a much greater advantage to have a regular pattern that wasn't going to disturb drivers through their randomness. The reason we only put them in 2 lanes, there were 2 basic reasons. One was an experimental, one was a practical reason. The experimental reason was we wanted to try and find out whether there'd be any pickup from one lane to the other, whether drivers in the unmarked lane would try and use the markings in the lane beside him. There was in fact a small amount of pickup, but not as much as the effect in the other 2 lanes. The practical reason for not marking the 3rd lane was because with the initial sites, because the public hadn't seen them before, we wanted to make quite sure they understood how to use them, and we felt it would be necessary to put signs on both sides of the road if we used all three lanes, because large vehicles can often obscure the near side signs. To be practical, it's very difficult to put a sign on the central reservation. It's not very wide. So that's the reason we didn't mark the third lane and we marked the other two.
If the pickup effect had been more marked, this is the sort of chevron marking you might have become used to. It's the brief time in Northamptonshire before they'd laid the near side lane pattern. The constant balance between making the chevrons an accurate tool and making them operationally simple is typical of the attention to detail necessary in communicating any model to a user. In fact, the spacing for different speeds is hardly a problem at all. Although based on 65 miles an hour and 2 seconds, using the chevrons at 80 miles an hour only reduces the time gap by just under 0.4 seconds. At 60 miles an hour, the time separation stretches by less than 0.2 seconds. But when we filmed in 1993, there were no definite plans yet for more chevrons.
Well, it may not be too long before we see more chevrons around. The accident effect was very encouraging. It was large. There was nearly a 2/3 reduction in accidents on this stretch of motorway. And what was most surprising was it was statistically significant. That was only 1 year of after data, and normally you'd be very surprised to get statistically significant change in such a short period of time. One of the more interesting and surprising elements of that accident reduction was the fact that single vehicle accidents were virtually eliminated. Now, this was a measure, of course, to reduce close following, for which you need another vehicle. But the conclusion we drew was that they act as a sort of alerting device. There's something extra for the driver to look at, for him to be interested in, and perhaps therefore make him that little bit less likely to have an accident. And we need to be really sure before we move on, and that's why we didn't start using the chevrons just on the basis of 1 year's accident data. And we're in the process of collecting a second year after data now. And what we're interested to see is whether or not that effect's been sustained or whether it's decreased. And if it's decreased a bit, that's okay, as long as we've still got a reduction.
At one level, this programme has been about road safety. But it's also traced a very realistic problem from a modelling focus. You started with a tightly constrained dynamics problem about cars. It was a perfectly respectable model, but observation showed that it didn't relate to how people actually behave. Modifying that model to give the 2-second rule introduced the problems in communicating the model to the users. Problems inventively addressed by the use of chevrons. This in turn raised the question of evaluating their effectiveness. Problems of communication and evaluation are typical of real modelling situations, as you will see in future programmes.